This is Mirabilis Design's webinar on network-on-chip architectures, exploring the power and performance of SoCs that use network-on-chip architectures. I'm Deepak Shankar, your host today, and I'm one of the founders of Mirabilis Design, a Silicon Valley-based software company that provides modeling and simulation software for architecture exploration of semiconductors, embedded systems, and software. Today's agenda is we're going to talk a little bit about on-chip communication, an introduction to system design and exploration and comparison to RTL design. We're going to then get into the details of network or chip, especially around the metrics that go into making decisions on the configuration of network on chip. And from there, look at the bigger picture, which is the actual SoC, which may not just contain network on chip, but may contain other elements like buses, switches, IOs, DMAs, memories, things like that. From there, we go into detail on exactly how a simulation model is constructed in VisualSim for a network on chip based SoC. And we would simulate it and look at some of the results and try to analyze to help make decisions on coming up with the right architecture or the right system configuration. Quick introduction to Mirabilis Design. We've been around since 2003 and are based in Sunnyvale, California. Our purpose is to really provide a system design and virtual prototyping platform that enables architects and system designers to very quickly create a model of their system and then be able to run a variety of iterations or trade-off studies to come up with really the project feasibility, specification that's been highly optimized, and provide a platform for universal communication. Mirabilis Design is in a variety of market segments extending from semiconductors, storage, communication, computing, aerospace and defense, automotive. The product is called VisualSim Architect, and we have over 55 customers worldwide with about 250 to 300 projects that have been completed with our product. One of the reasons that people purchase our product VisualSim is really about providing the right configuration to match your customer requests. That is what the solution does. And to enable that, we provide a large library of parameterized building blocks that allow you to put together system models very, very fast. The product VisualSim is a discrete event simulator based graphical environment where you can construct a model of your hardware, software, and the network connectivity, and then run a variety of analysis from timing, energy or power consumption, doing hardware software partitioning, and then doing specialty elements like doing failure analysis, the test or assertions for verification, generating traces for downstream analysis and studies, things like that. As I mentioned earlier, a large library of components is provided to help you assemble up your model very quickly. In addition to that, we do provide a library of interfaces to a variety of languages like C++ code, Java, Python. Also be able to connect to proprietary simulators, be able to generate traces either as a FSDB or a CSV or a text file. And probably the most important interface is being able to import and export into Excel. Being a graphical environment, we also have graphical debugging tools, analysis tools, reports that are provided as part of the modeling environment that's generated every time you run a simulation. Now, VisualSim itself, as you can see, is a completely graphical environment. It's got ability for you to enter in parameters. Each of these boxes correspond to a component in your system. In this case, we're looking at an SoC that goes with an Android-based hardware platform, not just for mobile, but for a variety of consumer applications. There are a lot of reports and analysis tools built into the environment that you can drag and drop and utilize. And finally, there is the most important, the power analysis environment that gives you a complete power profile down to the device, application, and the subsystem level. So this is a complete platform that enables you to assemble up your systems and then set up parameters for which you can do regression analysis through a parameter sweep process. Some of the statistics that are generated, and we'll be going more into it, is you can get statistics in terms of timing diagrams, the latency or throughput, and power consumption. You can also get textual statistics that give you things like utilization, delays, buffer occupancies, things like that, and also give you statistics on a per device basis to give you an idea of what the cumulative average power is and things like that. What this allows you to do is allows you to very quickly narrow down what my architecture is going to look like and also where is my system bottlenecks. So very, very quickly, it gives you visibility into that type of information. Now, VisualSim has a large library of predefined components. So it can range anything from processors to interfaces to memories to storage to networking components, but also a lot of components for you to build your own custom uh, elements, such as, say, a latch, which you want to define for your hardware, or say, for example, a buffer with an arbitration scheme has components to allow you to enable those as well. Now, one of the key things in VisualSim that allows you to do is be able to provide a universal communication platform. So once the architect has constructed the model, done the analysis, tested it, and fully validated, it can be embedded in your document that can then be utilized by anybody else downstream for actually analyzing the system or using it for demonstration or doing generating reports that can be used for marketing purposes, things like that. To give you an idea of how this environment works is I'm just going to open up a browser. Oops, sorry, I opened up the wrong one. There you go. So this is from our server in Florida, and as you can see, I'm actually bringing up these designs that have already been pre-built. In this particular case, it's an IoT-based architecture that I'm assembling up together or demonstrating out right now. So when you create a model, one of the things you have the ability to do is generate documentation right out of the model. So for example, over here, I can run this and I can immediately see what are the attributes that are associated with that particular component. Or for example, on some of the networking things. But what I can also do right out of the documentation is I can actually click on this launch button and bring up the simulation model right from within the web browser. So anyone that has a need for, say, they want to analyze their say their firmware algorithm, or they want to try to use a different NAND flash, or they want to try to use a different variation of the ARM processor, they just need to go change some parameters from within the browser, and they have the ability to get access to the model and be able to run simulations right from within your document itself. So it allows you to extend the use of the model beyond just the architect's environment. As you can see, it's coming up. The first time around, it takes a while to come up, but after that, it's extremely fast. So in this particular case, I also have a lot of bandwidth on the GoToMeeting activities. So that's another reason why it can be a little slow sometimes. So as you can see, this is a VisualSim model. You can see the libraries on the left-hand side. I can double-click on parameters, on blocks, and it can show up its parameters. All from within the browser, I can click on this Go button, and it'll actually run the simulation as well. So it allows you to be able to communicate across your entire design chain. Now, going back to the presentation, let's take a first look at the introduction to the network on chip. But before we do that, we want to look at all the possible on-chip communication components available. So when you look at common on-chip things, it can be network on chip, obviously, but you have point-to-point, token ring, crossbar, shared bus. There's a variety of different architectures. And the selection of your communication architecture has a major role in terms of what is going to be the size of the chip, how many devices you can connect, what is going to be the response times, what is going to be the total power consumption of the SoC. All of them have a major impact based on the on-chip communication that you select. Also remember that even though you might have a network on chip, it does not mean that the network on chip is the only interface on the or bus on the SoC itself. There might be a lot of legacy systems that might require PCI Express or NVMe Express, or might require AXI with an ARM processor. All of that will also have to be considered when you're looking at the SoC. Now, the specific topology or the specific communication interface that you need to use for your architecture really has a lot of the impact based on how many cores you're using, what type of cores, hardware accelerators. Are you looking at things like cache coherency? What is the available memory bandwidth? All of these lead to the main requirement of on-chip communication, which is the quality of service for all your communication. So it's between your master and slave. What is all the requirement that you have for your quality of service? That determines which on-chip communication architecture you try to deploy. Now, let's take specifically the network on chip. There's a lot of system design constraints in network on chip. Probably the biggest reason for migrating to network on chip is latency. You can actually define for certain streams to actually have an extremely deterministic latency, while the rest can have like a long lead time or a larger latency, which won't impact the system. So for example, if I was doing a video transfer or video processing, I'd give that something where you have a guaranteed latency or a configuration for my topology, and that way I could use a network on chip more effectively. This would be much harder to implement if you were using an AXI bus or an AHB bus or a PCI Express. The other aspect is really about power consumption, because one of the things with the network on chip is you can shut down large portions of the network. You can just turn on the devices that are currently active, things like that. Unfortunately, because the number of wires required, network on chip, the standby power tends to be extremely high. Now, some of the basic constructs of network on chip are like the buffers at each of the nodes, at each of the interfaces that are on the routers, the flit width, which is the packet sizes or the buffer widths that are being fed into the router, and then of course the asynchronous and synchronous bandwidths that are required. So this could be from the device to the router or from the router to router. The other big advantage of network on chip, which makes it very unique, is the allocation of virtual channels. And the reason for doing that, this is what guarantees either a bandwidth or a deterministic latency for each of the streams within your SoC. Now, the other aspect that has a huge impact on your design is really what is the size of the router that goes into these SoCs, and they have a lot of impact based on how many devices are connected, what's the distance from memory, things like that. And then, of course, the actual configuration of the topology is really dependent on how many streams are going to be running concurrently, what is the payload size, which is essentially what is the data size for your reads or writes to memory, and then, of course, what's the packet size that get broken down into the flit widths. Now, being a network, you do have a lot of arbitration and scheduling schemas that come into play. And you also have the routing table that you need to configure to put a system together. A lot of different topologies are possible using network on chip. So to give you an idea of what a network on chip would look like is something like this. So in this particular case, I just have a mesh architecture. I've got Each one of these routers have a device connected to it. That's my routing table. These are the basic attributes of these different devices. So for example, it's got 4 virtual LAN connections or virtual channels. That's the frequency, and then you can see what the flit size is, and then of course the buffering. So when I can construct a model using these standard components out of the library, and when I click go, a variety of statistics are going to come up based on the attributes that I've set up for those traffic generators that emulate the different emulate the different devices. So here, for example, you can actually see the buffer occupancy for each of the routers over here for the different directions that their connectivity is. But what you can also see is things like what is my end-to-end latency. Notice there's a spike in your response time, but after a while it follows a small range. So it says that the buffering is actually tapering it off so that you cannot have more data. Most likely it's actually dropping some data right there. Now what you can also see here is you can actually see what is the latency from node to node during that process, during the tracing process. So allows you to gain visibility into your entire architecture. So using this, you can connect different types of architecture. In this case, as I said, it's a mesh. You can make it into a ring architecture. You can make it into other types of architecture as well. These blocks automatically support that. As I mentioned, if there are any questions, feel free to ask the questions on our chat window, and there will be someone that can answer the questions immediately for you. Now, one of the key things to think about is when you're creating something new like a network on chip, is that you need to have a platform where you can explore or evaluate the different possible architectures. So one of the things we as in Mirabilis Design provide is a modeling and simulation platform. And this platform has a large portion of the components you need to assemble up the system. So for example, as I showed you, it has a router, and the router has buffering, timing latch, and static routing table. Also, as I showed you, you can actually change the configuration of the thing to go from a mesh to a ring to some other configuration. We also, as you saw a list, we also have a large number of library of components like PCI Express or AXI bus or AHP or NVMe Express or DDR4 or LPDDR or ARM processors or other types of technologies. So the idea is that you can actually take not just the network on chip, but actually assemble up the full SoC into your system model. One of the key aspects of network on chip, which is a major problem today, is simulation time. Because these NOCs get really large and the routers get really big, if you do a cycle accurate model, it tends to really slow down extremely fast. And that's one of the things that the library blocks that we provide you actually eliminates that problem, where it maintains cycle accuracy but still provides you the flexibility to try different regression simulations and do it very, very fast. Of course, as I showed you, a lot of reports automatically generated, quality of service, latencies, throughput, power, whole variety of technologies or analysis are reported out at the end of the simulation run. Now, why do you do system design? One of the reasons is in the past there was also always a dedicated flow from source to or master to slave. Now, in today's systems, you have a few different things. One is there's going to be a lot of contention on the buses. The second is there's going to be multiple concurrent tasks running that have to be scheduled, which means it's no longer just like this data goes to task 1, task 2, task 3, task 4 that does it in 4 different devices, but rather they're all distributed out, and they're actually competing for access to systems based on additional tasks or additional data packets that might be being processed through the particular system. So when you have something like this, the topology is really motivated by what is happening in your software tasks that are running on top of this particular system. So when you look at this particular design that we just showed you, we ran a simulation where we did a test between a 200 megahertz and a 400 megahertz. The 200 megahertz we found was, as you can see, higher latency in most of the cases, except in a few points here where the 400 megahertz actually took more response times. So what this brings you is that tells you is that if you just by increasing your bandwidth or increasing your clock speed does not necessarily mean that you guarantee better performance. It could be that there are other aspects of your system. In this particular case, the buffering at the cores that is causing an additional bottleneck. So, for example, if I move over to our environment and I open up that particular simulation model. So one of the things you'll notice in VisualSim is that we have a large library of demonstration systems, or what we call application templates, available in the environment. The reason is it allows you to very quickly build up the models that pertain to your particular system. So as you can see, this is the block diagram of the architecture that we saw earlier. These are the two software flows. We've got other types of statistics like the power tables, statistics, analysis tools, reports, things like that. We also have tables here that are the parameters that are used for regression analysis. We're going to go ahead and run the simulation. And one of the things you're going to see is that there's going to be a variety of statistics. So for example, this one here shows me the red line, shows me the average power, while these peaks here show me what my instantaneous power is. So one of the things you'll notice is that most of the time the power is in this below this range here, and just have a few peaks up here that actually increases my cooling cost that I have to be aware of. So this is something that allows me to know in advance, at least provide input to the mechanical guys on this is what my expected power consumption or energy is going to look like. You get other types of statistics, like for example, breakdown of how much of it is messaging part, which is the data transfer or data movement, versus how much of it was the actual processing. So if you look in application 1, you'll notice the processing is these red things, but the transfer, which is going across the buses, is the blue. While in the case of the application 2, you'll notice that the processing is a much higher percentage, while the actual transfer is much smaller. So this is only the transfer, while the light greens over here are the actual processing. So you can see one of them has more impact on the buses themselves, while the other one spends more impact on the processing resources. So you can actually evaluate where your bottlenecks are or what resources require more adjustment in your architecture based on a simulation model of this kind. And that's where you can really figure out where you're going to have these kind of unpredictable responses in your particular design. Now let's look at the network on chip. One of the things that you do in VisualSim is you don't actually build these models at an RTL or SystemsC level. Rather, you build it where you have the ability to define the entire chip right over here, but you don't actually put in, like, for example, each of the wires and things like that. Rather, you have your input port, you have your output port, which is resembled by this, an input buffer, an output buffer. It has the power, which is using our power library, but the actual data movement is done through what are called transactions. That's why we call this a transaction level model. Now, the actual data movement through the system still happens the same way. It still incorporates the latencies associated with the handshaking and things like that, but we don't have separate wiring here for mapping and reading and things like that. So if you look at a comparison between an RTL or a pin level model and a system model, the thing is that all the attributes, your width, your clock speeds, your buffer depth, your scheduling algorithms, your arbitration, all of that is maintained But what is not maintained is I don't have a pin by pin, rather I just send one transaction that actually takes care of all the pins and also takes care of the handshaking process. The data and control logic is still maintained. In some cases, you might still use addresses, especially if you're going to a flash or you're going to an SSD or to a DDR4 memory. Now, because we do this at system level, we get the same results, same level of accuracy, but then our simulation speed can be over 1000x faster. So this is the reason why system design is preferred for doing a lot of the architecture, and even a lot of the functional analysis is completed. As a quick note, there are people available to answer your questions. So if you have any questions, feel free to put them up on the control panel on the right-hand side. Now, let's take specifically the network on chip library that we provide you in VisualSim. If you look at any one of them, there are essentially about 5 aspects that you require to be able to define the network on chip. The first and foremost are the traffic generators, which essentially resemble the devices. The second are the routers. So for example, the routers have a variety of parameters: frequency, the coordinates, which is where it's located, the ingress buffers, the virtual channel buffers for each of them, the router addresses, the VLAN clock cycles for each of the virtual channels, things like that. The traffic generators themselves, you need things like, for example, what is a frequency rate, what is the data size range, because now we're talking about packets. What is the data size range? What's the flit width? Which VLAN is each one of these streams associated with? All of that kind of information. So this describes your topology and your host devices. Outside of that, what you do have is you need to have something that tells you what your VLANs are and what is the bandwidth, what is your static routing table, and then you have a series of parameters and statistics library components that are utilized for you to be able to run regressions and get the reports out. So these are the 5 elements that are required to assemble up a complete network on chip design. Now, these blocks here are fully scalable, where I could just build it up where I can just have 20 of these blocks, and it becomes a different type of a topology. So I do have the ability to very quickly create alternate topologies as well. Now, a variety of predefined reports. Some things show you the latency of the packets going from a source to destination, shows you what my end-to-end response times are, shows what the buffer occupancy is for each of the routers in each of the directions. So you can actually see which direction is consuming. Like, for example, over here, you can see the south port, router 1.1 and the buffer length. That's the one that's being buffered the most. And then you can see the green one, which is router 2.1. Notice there's like hardly any buffering. So this tells me that there's a lot of activity right now in the south port for buffer 1.1 and for buffer 1.2. So those I have to look at. Do I want to distribute the traffic to some of the other nodes as well? So that would be part of your regression analysis that you'd want to run. Now, an alternate to a very detailed or cycle accurate network on chip is, a lot of times people don't implement a very, very rigid network on chip. They use a more flexible mechanism where it's partially network on chip, partially a router, partially a switch, and then maybe partially even just an AXI bus. So what we've done is we provide you a variety of components. Of course, we provide network on chip, but this is more of a routing system with nodes associated with each of the destinations. Provide you this kind of a library where you can still get like the routing table, and you can get statistics on each of the links. You can get what your end-to-end response times are. While at the same time, you can also incorporate details of your rest of your hardware. As I mentioned, things like the AXI, the traffic generators, your process, things like that. Now, one of the key things you can do in VisualSim is what we saw until now was really about putting the performance together. and putting the functionalities, so like in terms of arbitration and scheduling. What you can also do in VisualSim is actually combine it with the power consumption in your system. Most times today, power is done using just an Excel spreadsheet or maybe some simple Python scripts. But one of the things we've noticed is you reuse the same thing, but then when you run the simulation in a more discrete event, dynamic simulation, what you'll notice is your expectation here, which could have been a combination of taking the average of these and putting it in, or taking the worst case, is completely off from what really ends up happening through the particular design. So as you actually are sending real packets through it based on different device requirements and based on their different commands, read and write commands to memory, for example, the power consumption will look drastically or dramatically different. So allows you to take an analytical spreadsheet model and extend it into more of a simulation-based power analysis. Now, when I look at power, there's a lot of reports that I can look at. Like, for example, I can see what the battery charge was. I can look at, what's the instantaneous power in the average, what was the application response time, what was the total power discharge. So it's a variety of statistics that can be generated right out of the power library. In addition to that, we also give you a trace of exactly what state each device was over the period of the simulation as a timing diagram, and also as an XML file that you can potentially import into an FSDB that can be used to run in your RTL environment as well for your power verification. We also generate a lot of these into Excel spreadsheets that you can then use for either for marketing or even for presentation purposes as well. Now, with this, I wanted to go into some of the demonstrations that we have constructed in VisualSim. So, for example, over here, what we have is we have an architecture that uses two different types of topologies in the same system. So, what you saw earlier on with the first design is it was purely a network on chip. So there was only one single technology that was utilized to assemble up the system. Now here what, for example, is, actually it's not the right model. Here, for example, I can combine a detailed AXI bus, and notice the number of parameters associated here to create a cycle accurate AXI bus, and combine that with a cycle accurate PCI Express, and I can enter in a DDR3 or a DDR4 DRAM block as well. So you can combine all of these within the system. You can even take it one step further, where the PCI Express could have an NVM controller running on top of the PCI Express. So it's possible that you can have your network on chip connect to an AXI, connect to a PCI Express which has NVM Express on top of it. So allows you to put your legacy, your new generation, and a network on chip all within the same design as well. Now, when you run some of these simulations, each of the simulations, depending on what it is that you're trying to do analysis, will give you a completely different output or a completely different statistics. So for example, over here, you can see it's showing you the statistics. I'm just going to let it run for a few seconds. Now this one is running for about 150 microseconds. So you can actually see here what was a read, which the red one is a write latency, the blue one is a read latency. This shows me my write throughput and my read throughput. This is on the PCI Express. This one here is showing me the read and write associated with the NVMe Express. This one shows me statistics on the buffers within the NVMe Express as well. So I can actually see that's the IOCQ buffer. You can actually see the different buffers in them, see what the value is. I can also get statistics on other types of subsystems within my thing. In this particular, it's also the same one. Oh, here we go. I can also get statistics on individual components. So for example, here the SSDs, It tells me what's the utilization of the SSDs and the memory within them, and what's the throughput I'm getting across those. I can also get statistics on any other devices that are there. So the main idea is that when I create a model and I run a simulation, I automatically get all these predefined reports that help me make decisions on what my topology or what my architecture should look like. So for example, same thing, but here it has an AXI bus as well. When I rerun this simulation, I'm going to get a completely different set of statistics out of the particular design. In this particular case, what I get is, in addition to the standard statistics, I'm also getting a detailed report, so like a trace on which slave, I get, like for each of the queues, who's doing, but I also get like, when the slave come in with the data, what was it to read, which ID, which source destination, what the data size is. So I can get detailed statistics or detailed reports on what is happening through the particular system. So that way I can identify if there's any system bottlenecks that might be occurring as a result of either a stream generating a huge amount of data, or there is very large size data, like say a video data that might be causing some of these systems to slow down, causing some other streams to have a more extended bandwidth, or a more a larger latency, while this video consumes a much larger bandwidth. Of course, there are other types of designs where I might have a complete SoC here, which has an ARM subsystem that is connected through a variety of buses that would have, like for example, the detailed pipeline and the attributes associated with defining an ARM processor. So again, this is taken out of our a block here called a processor generator that allows you to assemble it up. Similarly, you have cache blocks that you can set up in each of the network on chip destinations, and that way build up your cache coherency as well, where it connects up to an external DDR memory. The power table over here, extremely detailed. For each of the devices, you can have any number of power states. You can have transition times. You can have power management algorithms that you can define here. In this particular case, if it's sitting in standby for a certain period of time, I can move it immediately to an idle state. One of the things with the network is that if it's not doing anything, it's still consuming a huge amount of power. So you want to be able to utilize technology that can shut down the power completely to some sections of the network, or maybe to some of the routers themselves. So allows you to be able to experiment with those kind of attributes in your system. The other aspect that you can also look at when you're looking at these designs is the address table, which actually is my routing table, which tells me what is the connectivity between all my components. So even though I have, say, from here, I can go through this path to this destination, or I can go to this path to this destination. My static routing table, unlike a network, like an internet network or an IP network, here we tend to use a static routing table. And in addition to that, within each of these routes, we have the virtual connections, or your virtual LANs, and you have assigned bandwidth for each one of these channels. The reason that's important is, for example, in the traffic generator, I can actually specify which channel or which virtual LAN do I want to send it across. The reason that that is important is because then it allows me to ensure that certain elements get higher bandwidth, certain streams get higher bandwidth, certain streams get very deterministic latency. Allows you to run with those kind of experiments, or creating those kind of configurations. Similarly, when I go to the router, I can also get the buffer capacity, I can get the buffers, I can get the router frequency, things like that. Now notice one of the key things over here, the router frequency would be completely different from the network on chip frequency. So like for example over here, notice the router is running at 800 megahertz. The frequency for the devices is running at 5 megahertz. So there is a big difference between, like each one of them could be running on their own clock boundary. There's really no restriction there on all of them having to be the same, and which typically in the case of a network on chip, you have both synchronous and asynchronous clocks in your system. So you tend to have different types of clocks within your architecture itself. The reason you have these parameters is because now, once you're happy with the model, you save the model, you're ready to go, you have the ability now to actually run regressions where you can spawn off a large number of simulations with a variety of statistics. I'm sorry, with a variety of parameter values. So for example, just simple things is flit size. I can go with 16, 32, 64, 128. Frequency, the router frequency, I can try what happens if I have 200, 400, 600, 800 megahertz. Or ingress buffers. I could vary those ingress buffers and try, how much capacity or buffer backup do I really need to ensure no data is lost, and also to ensure that I'm getting the bandwidth and I'm getting the timing performance that I require. So using the environment, using the building blocks, you can very quickly put together the whole system and thus be able to do a variety of analysis. So with this, I want to conclude today's webinar on exploring the power and performance of network-on-chip architectures. With this now, I'm opening out the webinar to questions, and so feel free to ask the questions at this point.